In this video, we're going to reverse engineer the savegame file format of Commander Keen 6, so we can make a savegame editor. Let's start by opening up a savegame file in a hex editor. At first glance, we recognize a couple things already. The file seems to start with a magic number, CK6 and a null character. We also see the title of the savegame I entered in the game, Blue Waters Crossing, and we also see a whole bunch of semi-repetitive or at least patterned data. When we think about how the game behaves when loading a save game, we know it restores it perfectly. When Keen, at the time of saving, was sitting down reading his book in idle state, loading that save game will have him in the exact same position. Same goes even if he is midair, jumping around, the game will reconstruct that exactly. When we consider the file size of an average save game, around 15 to 25 kilobytes, we can assume that the game takes a snapshot of the current level and dumps it integrally in the save game. That would explain the massive amount of data we see here. First, let's focus on the easy and obvious values, things like the amount of lives, ammo, as we can see here in the status screen in-game. I have a score of 100 points, or 64 hex, 3 lives left and 5 ammo. The extra life counter is at 20,000 points, which is 4e20 in hex. It doesn't take long to find the extra value, but we have to be careful to swap the bytes around because of NDNS. A value of 4e20 hex will be stored as 24e in the file, as we can see here. Our 5 ammo and score of 100 or 64 hex can be found easily as well. As for the amount of lives left, we can't be exactly sure, as there are multiple values of 3 in this little clump of data. While we could manipulate these values in the save game, load it in the game and see what changed, that process could become very tedious very quickly. Instead, let's look for these values in memory while the game is running. We'll search for the values of the score, extra and ammo, who are neatly positioned one after the other. Our search string is therefore 6400024E0005. We're in luck, as we immediately find a match. Not only do we find our 3 values, when we compare the entire block of data with our save game, we see the entire chunk is there. The game does indeed copy this entire block of memory into the save game. The next step is now to play the game, shoot some bullets, lose some lives, and start mapping out what all these values mean, presuming they represent the game state. Keeping an eye on a flat piece of memory like this is a bit awkward. Let's just map all these values into a struct and look at it like that. We'll start by just assigning 16-bit unknown names to all these values, except for the ones we know for sure, which is score, extra, and ammo. As you can see, when I shoot a bullet, the ammo decreases from 5 to 4. I can also change the values directly in memory, and they will be reflected inside the game. Now, with some gameplay, we can deduce what most of the values represent. Let's go over these values and see how I was able to determine what they were. First, we have the Fribulous Zax, which is the overview map of the game, X and Y positions. While it might not be obvious yet as to why these resemble X and Y positions, later on, when we investigate entities in the game, it will become more clear. We notice these 2 values only get updated as soon as we start a new level from the map. This also makes perfect sense, of course. When the game loads in a save game, it needs to know where to put Keen on the overview map in case you are in a level. After you exit the level, Keen is positioned right outside the just completed level. This is that XY position. Then we have an unknown, along with some other unknowns a bit farther down. I have not seen these values change during many playthroughs. They might be padding, unused, or leftovers from unimplemented stuff, or I simply haven't found a trigger for them to change. When we force these values to, for example, OXFFFF in the save game, no weird behavior is noticed during gameplay, nor are the values zeroed out or changed in any way. They simply get loaded and saved along with the rest of the values. Next, there are 17 finished level bool 16s, which is a boolean stored as a 16-bit value. These simply get set as soon as you successfully finish a level. Note that the Bean with Bacon Mega Rocket level also gets a boolean, even though you can revisit that level as many times as you want. The unknowns after the 17 levels might just be room for more level completion booleans. Many of the remaining values can be found in the game's status screen. The rope and grappling hook, as well as the sandwich for Grapiter, are not just Boolean values. While a value of 1 and 0 means, respectively, that you either have the item or not, the game needs to remember whether you used it on the map. That's when these values are changed to 2. The game also needs to remember where the rocket actually is. It can either be on the mainland or on the space station. Finally, there's a pointer that was a little bit harder to figure out, namely the pointer to the platform you are currently standing on. It points to the platform entity itself, which we'll delve into later. While we could end our save game editor right here, just manipulating things like lives and ammo, etc., I want to take it a step further and visualize the snapshot of the current level itself. We're not even sure what the rest of the data in the save game represents. We're still going on the assumption that it's the tiles of the current level. The way to determine whether this is the case is to parse the game maps file, which contains all the pristine levels of the game. We can then see if the data resembles the unknown block of data in our save game. Luckily, lots of people, in particular Andrew Durden, have worked on reverse engineering the Keen games, and level editors do exist, so how the levels are stored on disk is quite known. The information can be found on the Shikadi modding wiki. There's 2 things we need to accomplish: extract all the tiles and sprites from EGA graph, and decode the level files in game maps. Let's start by extracting the sprites and tiles from EGA graph. The EGA graph.ck6 file consists of chunks, which are individual items the game needs to access, such as sprites or tiles. To know where these chunks are located within EGA graph, we use EGA head. This EGA head file is simply an array of 3-byte offsets. If you want to know where chunk 500 lives in the EGA graph file, you load the 500th set of 3 bytes in EGA head and you will find your offset. That's quite easy to parse. We can also figure out how many chunks there are by dividing the EGA head file size by 3. That's the size of our array of chunks. It is important to note that each individual chunk is compressed with Huffman compression. The Huffman table can be found in EGA dict.ck6. The implementation of the Huffman decompression algorithm is beyond the scope of this video, but not hard to implement. You can find some details on the wiki about this as well. To help with the Huffman decompression, each chunk, well, almost, as we'll see later, starts with a 32-bit value indicating the decompressed size of the chunk. When we look at what the wiki has to say about the contents of the EGA graph file, we see we have to skip a couple things first. Even though we know what the offsets of each chunk within the EGA graph file are, we don't know which chunks represent what exactly. The picture table, mask picture table, and sprite table are easily skipped. They are just 1 chunk each. We do need to parse these as they contain information we will need in a bit. The picture tables will, for example, give us information on how many pictures there are, and the sprite table the amount of sprites. Both picture tables just consist of pairs of 2 16-bit values, the width divided by 8 and the height, 1 set for each picture. We just divide the total chunk size by 2 times the size of a 16-bit value. The sprite table consists of entries of 18 bytes long, so we do a similar calculation to the size of the chunk to determine the amount of sprites in the file. Then we have the fonts, which are stored in a variable amount of chunks, 1 per font. That means we have to parse the actual chunks and determine whether it is a font or not. Luckily, the wiki has information on what the font format looks like, as well as a heuristic to determine whether we're dealing with a font or not. Basically, a font starts with a 16-bit value, 64 zeros, and then the value OX302. That's easy enough to detect and skip the font chunks. Next are the pictures and masked pictures themselves, each in their own chunks. We determined the amount of each by looking at the size of the picture tables, chunks 2 and 3. These picture chunks can then easily be skipped as well. Finally, we end up at the sprites themselves. We know how many sprites there are, we know the chunk index of the first sprite. Now all we have to do is Huffman decode each chunk, interpret the graphical data, and write the sprite out to a PNG file. Of course, things aren't that easy. First of all, the data is not stored as RGB8 tuples, but rather as raw EGA data. The wiki has some information on how to interpret this raw data. It presents multiple options on how the data is stored, so we have to experiment a bit to find the correct one. For Keen 6, it came down to 5 planes of data stored one after the other, for respectively mask, blue, green, red, and intensity. How to convert these BGRI values to regular RGB is through a palette, as can be found on the wiki. Pick the correct column that matches your BGRI values, and the actual color is in the results row. The mask bits then of course determine the transparent pixels. One important detail about the planar data for the colors is that one pixel does not take up 1 byte, but just a single bit. That's why the width in picture and sprite tables will always be divided by 8. To decode, you have to treat the values bit by bit, not byte by byte. If you decode everything correctly, you should end up with all the sprites in the game. Next in the list we have the 8x8 tiles, which we don't really need to extract, as the wiki says they are mostly used for dialog borders and status windows. If you do want to decode these, you have to take into account that all masked 8x8 tiles and all unmasked 8x8 tiles are each in their own chunk. Only 2 chunks for all these 8x8 tiles, so you have to determine the amount of tiles yourself by looking at the total chunk size and the size of either a masked 8x8 or unmasked 8x8 tile. The 16x16 tiles are the ones we are after, as they will make up the levels themselves. Each tile is an individual chunk, but there are 2 major problems. The wiki casually mentions these problems as follows. These chunks do not have a D word specifying their decompressed size, as this is hard-coded into the executable as a space-saving measure, as is the start and finish of unmasked and masked tile chunks. First, for the Huffman decoding, we need to know how big the decompressed data is, otherwise the algorithm will happily keep decoding until it runs out of data. This information being hard-coded in the executable seems something that we'll have a hard time finding, which doesn't make things easy. The second problem, not knowing where the masked tiles stop and the unmasked tiles begin, or vice versa, is not that hard to solve. We know the width and height of the expected tile, so we only need to test whether there are 4 or 5 planes in the presented data. The unmasked tiles will not have a mask plane, so we just divide the chunk size by either 4 or 5 planes worth of data. Whichever of the 2 yields a round number indicates what we are dealing with. Let's tackle the first problem by looking in the executable. Before we can even think of loading the Keen 6 executable in Ghidra, we need to decompress it, because the game itself is compressed with lzexe. Luckily, there's a unlzexe GitHub repo available, which provides a decompressor. Just compile the C file and decompress the executable, which we can now throw in Ghidra. The assumption we make to find our hard-coded decompressed chunk sizes is the following. The Huffman decompression routine in the game needs to know these sizes, otherwise it wouldn't have enough information on where to stop decompressing, just like our own Huffman decompressor. If we can locate the Huffman decompression function in the game, we can see who calls this function and with which parameters, of which the decompressed size will be 1. Now, our problem becomes finding the Huffman decompression function. One piece of information from the wiki helps us with this. It mentions the Huffman dictionary being either embedded in the executable or as an EGA dict file next to the executable. Even though I had my EGA dict file present next to the executable, it was worth a shot to see if that dictionary also existed inside the executable. A simple search proved that the executable did indeed contain the copy of the Huffman dictionary, something the Huffman decompression function surely needed access to. Looking up those bytes in the running game, a match was found at address 38BE65BE. Notice the segment in Ghidra being off by hex 1000. If we could put a watch point on this address and see what the program counter points to, found in registers CSEIP, then we could see where this data was accessed. Unfortunately, DOSBox X doesn't appear to let me set a watch point or a read memory breakpoint, so we'll have to create our own. When we look in the source code of DOSBox X, we find that paging.h has 3 interesting functions: memreadB inline, memreadW inline, and memreadD inline. These are to access a byte, word, and D word. Let's inject our own logging in that function, dumping the program counter at cs::eip, while our specific address 38BE65BE is being read. We just have to convert the segment offset address to a linear address and compare that to the address being accessed by the game. Now we launch the game, and immediately we see the memory location being accessed many times, but always from the same spot, 1A790361. Knowing that Ghidra's segment was off by hex 1000, we can look at 2A790361, where we find ourselves in a big function that does the Huffman decompression. How do we know this is the Huffman decompression function? There are a couple indications which require knowledge of how the algorithm works. The occurrence of this pattern indicates the going left and going right in the Huffman algorithm. You'll see this happening twice, as there's a big if clause that divides this function in two. This is merely because of addressing reasons. Both blocks perform the same decompression. It's interesting to see that param5 seems to be used as our decompressed size parameter. In the if block, the stop decoding address for decompression is calculated in PU_var3, being param3 plus param5, and the exit condition is whether param3, which is incremented each loop, is equal to our end position. In the loop of the else block, param5 just gets decremented and checked for it being 0 to exit the loop. All we now have to do is look at all the functions that call this decompression function and see which value they pass for parameter 5. Ghidra neatly lists the higher up functions that call this decompression function. We see 6 call sites in 4 distinct functions. When we take a look at the first, it becomes obvious that this is not what we're looking for. The 5th parameter, the decompressed size we are looking for, is hard-coded value OX94. While the next 2 of the 3 remaining call sites don't have hard-coded size values, the final call site looks to be most promising. If we look at the call to the Huffman decode function at the bottom, we see that local 6 is the parameter we are interested in, being the 5th parameter indicating our decompressed size. When we look higher up, we see local 6 being set to various values based on what the incoming param1 is set to. Param1 is then obviously the chunk index. This is a getChunk function where you pass in the chunk index and output buffer pointer, and it Huffman decompresses the chunk for you. 2 interesting things to remark here. Remember, the 16 by 16 tiles not having the decompressed chunk length as the first 16-bit value was the exception to the rule. All other chunks start with their size in EGA graph. This can be seen in the first if clause, where local 6 is not set to a hard-coded value, but rather taken from the first couple bytes. Secondly, the game checks whether the requested chunk index is less than hex 15AE twice. The second else if block can therefore never be reached and is dead code. This is not a misinterpretation by the Ghidra decompiler. The assembly shows the same pattern. At this point, we have all the information we need to extract the 16 by 16 masked and unmasked tiles from EGA graph. Decoding the graphical data is the exact same as the sprites, with the added caveat, as mentioned before, that we need to determine the plane count so we can choose between masked and unmasked. Now that we have extracted all the relevant sprites and tiles, we move on to the game maps file, which contains all the level data. Again, we rely on the wiki for information about the game maps file format. Similarly to EGA head, which contained all the offsets of the chunks inside the EGA graph file, the game maps file is indexed through a maphead file. Unfortunately, there was no maphead.ck6 file present in my version, so it has to be embedded in the executable. The maphead data can be easily found though, as it starts with a magic word for the RLEW compression used to decompress the level data. This magic word is hex ABCD, so we simply open the executable in a hex editor and search for CDAB, swapping the bytes of course because of endianness. According to the wiki, the magic word is followed by 132-bit pointers or offsets into the game maps file. Considering we only have around 17 levels in the game, we can assume the rest are zeros. There's 3 matches on CDAB in the executable, and the first 2 do not match our assumptions above. The third one does. After the 100 game maps pointers inside maphead, we can find the tile info data, which we will leave for later. Now that we have an offset for each level in the game maps file, let's start parsing the data found at these offsets. Every level starts with a level header consisting of the following information. 3 32-bit values containing the offset within the game maps file of the 3 compressed planes of level data, 3 16-bit values containing the lengths of the 3 planes of data, 2 16-bit values indicating the width and height of the level, and 16 characters containing the internal name of the level. There are 3 planes of data in each level: a background tiles plane, a foreground tiles plane, and an info plane. All 3 planes of data are doubly compressed, first with Karma compression, then with RLEW compression. How these compression schemes work is also beyond the scope of the video, however you can find an implementation of both algorithms on GitHub. Now it's just a matter of decompressing the 3 planes twice and visualize them. Each 16-bit value in the plane refers to the index of the tile. This is not the same as the chunk index, however. The 16 by 16 tiles start in our case at chunk 438, so if the background plane refers to tile 0, that will be found in chunk 438. While the background plane refers to the unmasked tiles, the foreground plane uses the masked tiles. To make things a bit more difficult, the tile numbers specified in the foreground plane reference the start of the masked tiles. As mentioned before, the start of the masked tiles is hard-coded in the game, but we had a solution for that. We just loop all the 16 by 16 tiles, and once the plane count shifts over from 4 to 5 planes, that is the reference index for our masked tiles. In our case here, that is at chunk index 2815, that being the first masked tile. If we subtract 438, the first unmasked tile, from 2814, the last unmasked tile, we know there are 2376 unmasked tiles in the game. Now, as an example, when the foreground plane mentions tile hex 4E1 or 1249, which refers to a tile that is part of the cockpit of the Bean with Bacon mega rocket, we know it only starts counting from the start of the masked tiles. So, to know the tile index within all 16 by 16 tiles, we add 2376. This tile can be found at tile index 3625, or if you want to know the chunk index, just add 438 to end up at chunk index 4063. Now we can just paint the background plane first and then the foreground layer on top. If we take another look at the save game file, we notice something about the blob of data after the game state. We see multiple instances of CDAB sprinkled all over this data. This is an indicator of RLEW compression. And yes, when we try to decompress this data, the same way we handled the game maps levels, we find that this data does indeed contain the 3 planes of the level. The only difference being that the save game does not have the double compression applied. There's no Karma compression in play, just RLEW compression. It's just the raw data of the planes though, nothing more. There's no header, as there was in game maps containing the level dimensions. So how do we know the level size, and thus the decompressed size of a plane, which we need for the RLEW decompression algorithm? Simple. In the game state, we find the location field, which contains the level ID. We simply make a lookup table of level dimensions, and we have all the information we need to decode the 3 planes. The only things that are missing now is Keen and his adversaries, and all the other sprites. When we see how far we have gotten in the file, after parsing the file header, game state, and 3 planes of tile data, we see there's a bit of information left at the end. Surely that must contain information about all the sprite entities in the game. Here we see the final part of the save game file. We're assuming this is going to be an array of sprite entities, and each entity would need to have several parameters associated with it, such as its type, sprite ID, X and Y coordinates, etc. What we'll do is load up the save file in the game and search for this data in RAM. Again, we'll assign a struct to each entity, which will help us figure out what the fields of each entity represent. The only thing is, we have no clue how big this struct is. In other words, how many fields there are. If we look closely at the data, we see randomness, but in a way, it also seems structured and organized. This leads me to believe that all the entities have the same amount of fields. Each struct is the same size. We can estimate the length of the struct by counting the amount of bytes between recurring patterns. Notice the pattern of these highlighted bytes. We have a value followed by a 0 followed by 8 bytes and another 0. When we measure the distance between all these arrows, something interesting comes up. It's always 76 bytes. This cannot be a coincidence. There's a high chance of this being the sprite entity struct size. two more things we can test about this assumption. First, if we fill up this struct with 16-bit values, we see that exactly 38 of them fit in one struct, 76 divided by 2 bytes per field. Of course, there are no guarantees that the struct is solely made up by 16-bit values. It gives us merely an indication. Secondly, we look at how much space we have left in the file. In this example's case, the total file size is 21,074 bytes, and the list of presumed entities start at offset hex 3 EBA or 16,058. This leaves 5,016 bytes for the entities list, which, if we divide this number by the size of what we think is one entity struct, 76, we get a round number of 66. This would imply the savegame file has 66 sprite entities in it. When searching for the entity bytes of the savegame in RAM, after loading up the save, we find this batch of data at address 38BE 75CE. It seems this chunk of data is integrally copied into the savegame file without any compression. I've mapped several dozen entity structs onto that memory, and this is the first one. Watch the values change when I move Keen around. Apparently, the first entity slot is reserved for Keen. There are quite a few values that change in response to walking and jumping around. It doesn't take long to figure out that unknown 6 and 7 are the X and Y positions. They do seem to have high values though, around 5,000–6,000, where Keen is currently positioned. A bit further down, we see more numbers change according to position, but they are much lower values in the 10s and 20s. Those, however, we can already figure out. They're the tile coordinates. Now that we can render the layers of the level, we can easily look up tile coordinates and they match up perfectly. The tile coordinates are two cores for tracking Keen's position. He would be jumping around tile per tile if that indicated his position. The large numbers representing the X and Y position are simply the tile position times 16 times 16, or times 256 of course. This gives a more precise coordinate system to position entities in the level. In the middle of all the fields are 5 high-precision coordinates and 5 tile position coordinates that all change when Keen moves. The high-precision coordinates differ slightly from the X and Y coordinates at the top. If we calculated the offsets of these values respective to the XY coordinates, we can determine that these represent the hitbox of the entity, both available in high precision and in tile coordinates. The other interesting part of this entity is in the last two unknowns, 37 and 38. For Keen's entity in the first slot, these are hex 761A and 0. Let's look at the values for the second slot. We'll ignore for a moment the fact that even though this entity has XY coordinates, it has no hitbox coordinates. I believe this is the camera tracking entity. Look at unknown 37 and 38 again. This time, 38 is not null, but has value hex 75CE. This number rings a bell. That's the address of where we found the first entity in RAM. Looking at the value for unknown 37, which is hex 7666, we can see that this is also a RAM address pointing to the entity in the third slot. So, unknown 37 points to the next entity slot, and unknown 38 points to the previous one. This, of course, creates a doubly linked list. It also makes sense that the Keen entity in slot 0 does not have a previous pointer, it was 0, as it's the head of the linked list. The last entry in the linked list will then similarly have 0 for its next pointer. The fact that these previous and next pointers match up exactly to the slots we have allotted for each entity proves that our guess of 76 bytes per entity was correct. These two pointers are the last fields in each entity. After playing around with the unknowns a bit, here's what I came up with, what I think most of them represent. I guarantee there are mistakes in here. For example, the in-air velocity, level loading transition, z-order, etc. There are some mystery pointers in there as well, and it seems some entity fields have different meanings in different entities, or on the overview map compared to in levels. While it is fun to figure out all these values, for the savegame editor we mainly need type and position. The goal is to render the level with all entities in it, as well as to move entities around and create new ones. We figured out the coordinates and hitboxes, which we need to position our entities in the level and adjust them when moving entities around, and we figured out it's a doubly linked list, so it's now trivial to add new entities to the end of the list. Before we create our savegame editor, we need to take a look back at the file header. We know it starts with CK6 and a null character, and it contains the title you typed in the save screen, but there are some unknowns in there as well. To find out how many characters are reserved for the title, we can simply enter the longest string we can in the save game interface inside the game. My go-to way of doing this is to put the entire alphabet in there. Looks like X is the final letter, that makes for 24 positions. But then, when I was testing other stuff, I saved my file with a title consisting of numbers 0 through 9 multiple times, making it also easy to count. Suddenly, only 22 characters fit. Then, I realized that they are limiting the amount of characters not only by the buffer size, but also the width of the input field in the interface. No need to implement scrolling the input when the title is wider than the input field. Easiest solution to figure out the buffer max size is then to repeat as many thin letters as you can. This is the max amount of the letter L the game lets me enter in the field, so that must be our max buffer size, 32 characters plus presumably a null terminator. This leaves 1 byte of padding before the game state struct starts with hex 77, 29, 00, 3b, etc. There are 2 unknowns left between the magic value CK6 and the first letter L of our title. The first value, 1AE8 or hex E8-1A, is a file version. Opening a save game file from game version 1.5 in version 1.4 or 1.0 is not possible, and vice versa. This number, which is hard-coded in the executable, prevents save games from other versions being loaded. The numbers for the different versions are hex A339 for version 1.0, hex A6C5 for version 1.4, and of course hex E8-1A for version 1.5. The remaining 16-bit value between the version and the first letter L of the title remains a bit of a mystery. In this example, it is set to 1. I think this is only set to 1 when you overwrite a pre-existing save game. If you save in an empty slot, this value is set to 0, and if you overwrite a slot where there's already a saved game, it is set to 1. The question remains, why would they need to know this information? Even though it might have something to do with the problem I will explain next, I am still not convinced, as I can parse the entire save game without issue, even ignoring this flag. The mistake I made trying to parse out the list of entities at the end of the save game file was the following. I wrongly assumed the entire block of memory from first to last entity in the list was dumped inside the save game. That would mean there were either garbage entities or gaps between entities, but since the entire block could just be copied in memory at the same spot by restoring the game, those gaps wouldn't be an issue, as the integrity of the pointers in the linked list would still be valid. I would simply start at the entity list in the save game, read the first entity and look at its next pointer. To find the second entity in the save game, I would calculate the relative offset in RAM and use that to relatively offset inside the save game. That way, garbage entities or gaps would be skipped. The first problem I encountered was that sometimes I would get entities with weird data in it. Granted, they could be garbage data or uninitialized memory, but some appeared after the last entity in the doubly linked list, the one with a next pointer of 0. After a while, I realized that when saving, the game doesn't bother to rewrite the file on disk from scratch. It just opens the existing file if it exists, dumps the save game contents, and that's it. If you have a level with 70 entities, as is the case at the start of Blue Waters Crossing on easy difficulty, you get a file that's about 24 kilobytes. Then, when you go to the map and overwrite the save game file, the file size does not change, yet there's only 9 entities on the map. This implies that you can't just blindly read in chunks of 76 bytes and load those as your entities. You have to respect the doubly linked list, as in, read until you encounter an entity that has 0 as its next pointer. And yet, I still saw some garbage entity data, at least sometimes. When following the previous and next pointers in the save game, the problem became obvious. The garbage data started as soon as there had been a gap in the entities. Instead of leaving the gaps inside the save game, the game just runs through the doubly linked list and dumps them sequentially in the file. My whole approach of relatively addressing RAM and save game offsets was incorrect. When restoring, the game knows exactly where the first entity goes. When reading all the next entities from the save game file, it just needs to look at the previous pointer of the to be inserted entity, Look that up in memory and look at its next pointer. That will be the address the new entity needs to be written. Repeat until you encounter next pointer 0 and you're done. I did not verify in the disassembly that this is the exact way it works, but it seems reasonable to me. So, if this is the way it works, why does the game need to know whether it's an overwritten save game or a pristine save by setting the flag in the header to 1 or 0? If you follow the algorithm correctly, surely there's no chance to end up in potential garbage data left over from a previous save at the end of the file. I wanted to make the save game editor capable of placing new enemies in the level. An Orbitrix in Blue Waters Crossing, for example, which is what I added to this save. While adding a new Orbitrix entity in the doubly linked list is child's play, the game crashes when the Orbitrix moves into view. It seems the game crashes when you try to load a sprite it wasn't aware of. I assume the game only loads the sprites in memory that are defined in the third info plane for each level. The question is, which third plane? Either the one from game maps containing the pristine levels, or the one that is supplied in the save game file. If it were the latter, we could just add a spawn point for a previously non-existing enemy inside the level somewhere, and it would pre-cache the sprites. Unfortunately, after trying this, it doesn't work. It seems the game loads the possible enemies either from the game map's spawn points, or there's a hard-coded list inside the game somewhere. For now, I've solved it by only allowing the creation of new enemies that already exist in the level. Adding new enemies to the level works simply by adding them to the doubly linked list. But for some types of enemies, there's an extra problem. Some of them expect to be placed on solid ground. If you spawn them in air, the following will happen. Enemies that can fly or jump don't have this problem, but most of them do need to be on solid ground to function correctly. So we need to create a snap function in the save game editor to position new enemies or dragged existing ones on the floor. We can simply look at the second plane of tile data, which represents our foreground tiles. There's an issue with that though. Note that Keen is not standing on the topmost foreground tile. If we just drop his hitbox on the first foreground tile we vertically encounter when dropping him from a height, he would be standing on the top tile. There has to be a way to determine whether a tile is fall through or not. Of course, Keen is just an example in this situation. You can place him anywhere in the sky and he will immediately start falling. He won't wiggle like the bloop did. Of course, the wiki has the answer for this problem. Remember when we were parsing the game maps file, we needed the information from maphead to determine the pointers to the level data inside game maps. After those 100 pointers is the tile info data. The wiki has an entire page devoted to this. After the 100 pointers, there are several planes of data consisting of 1-byte flags with properties related to all the tiles. The wiki tells us the following planes are in play. Luckily, we already know the amount of masked and unmasked tiles we have, so we can easily determine the size of all the planes and skip right to the one we need, the masked top plane. Masked because we are interested in foreground tiles. The top plane defines whether a tile is flat or which direction it slopes, but more importantly, it also lets us know if a tile is fall through. This is exactly what we need to make an enemy land in the right spot when dropped. The save game editor is however not perfect. Dropping or spawning a gravity-bound enemy in the wrong position and make it wiggle when loading. Best to place your enemies on flat ground. So there we have it, the save game editor is now functional. We can change all the game state variables, move sprites around and add new enemies to the level. If you want to try it out yourself, you can find a link to the save game editor in the description. I've also created a blog post with all this information and added a recap of all the fields found in the save game. If you see any errors or have remarks, you can always leave them in the comments below. You can find a link to the blog post in the description below as well. The goal is to extend the save game editor to support more Keen games, which I will live stream in the future. Be sure to follow me on social media if you want to be kept up to date. Thanks for watching.